Hello and welcome to the industrial classroom. In the previous class, we had studied about the basics of the industrial hydraulics. We went through the uh, various themes like the pressure, the force, and also we studied about Pascal's law. Let us today move into a little bit of depth and extend the class. The first thing, without wasting a topic, let us start with the atmospheric pressure. These are the basics, and just after this, from the next class, we will dive into the industrial hydraulics. And today's class is very much important because you will get the knowledge of some of the most important concepts that are very important for the hydraulics and for the basics. So, first is the atmospheric pressure. See, here this is the earth, right? It is the earth, there are some of the continents here, and it is surrounded by a film of air, a blanket of air, which is the atmosphere. Like from starting from the troposphere, stratosphere, there is different zones of the atmosphere. This layer of air also exerts a pressure on the earth, on every aspects of the earth, not only human beings but also oceans, trees, everything. This pressure that the atmosphere exerts on us is called the atmospheric pressure. If we define it, we can say that pressure exerted by the weight of air column on a unit area. For specific area, let us this will be the earth, and if we consider a small area, then the amount of weight exerted on this area we will call it as atmospheric pressure. It is provided by the air column. Remember, this air column is there, therefore it is atmospheric. Next, for basic measurement, we say that it is around 760 mm of Hg. If you put a inverted glass tube here, and here I have put a bulb or perhaps a beaker. Okay, now here I have filled with mercury. To know the atmospheric pressure, this is filled with mercury, right? Liquid, which is liquid at room temperature. When there is a pressure, when we can see that there is a rise in the level of mercury inside this glass tube. Okay, when the pressure decreases, okay, when the pressure decreases, the rise, it will also decrease. When the pressure will increase, the level of mercury will go much higher. Okay, so this is a simple demonstration of the fact that there is a pressure exerted by the atmosphere. Okay, for basic concepts, you must know that it is equal to 760 mm of Hg, which is equal to 10.3 meters of water. So large, therefore mercury is used. Since density of mercury is much larger, density of mercury is much larger than density of water. Therefore, mercury measurement in barometer 760 mm, it is quite small as compared to 10.3 meters. It is very means predicted to be impossible, right? Next, which is equal to 1.033 kg per centimeter square, is equal to 1.01325 bar or 14.7 psi. Next, if we look at the atmospheric pressure, we can generally let us make a drawing. So this is the what? This is the atmospheric pressure. Let me write it as PATM. Okay, this is the atmospheric pressure. Now there is a zero pressure line, okay, which is termed as the P absolute, at absolute pressure. Okay, now whenever you are measuring some pressure, okay, we have a pressure gauge in it. We have a pressure gauge in it for any industrial line. Let us consider for a air blow, for a air compressor. We have a air compressor, we have a pressure gauge here. This is the gauge which detects the pressure in it, pressure of the air content in it. Remember that the gauge pressure does not measure from absolute zero, it measures from the atmospheric pressure. So gauge pressure is somewhere above this atmospheric pressure. Okay, gauge pressure is somewhere above this atmospheric pressure. So here what you see, gauge pressure, the pressure measured relative to atmospheric pressure, means with compared to atmospheric pressure, it is the gauge pressure. Gauge pressure always shows zero at atmospheric pressure, means for this gauge pressure, this PATM, it is zero. Okay, when we will go to P absolute, the gauge pressure will be minus. So we won't consider it because this meter reading will not go negative, right? Therefore for the gauge pressure, what will be the 0 point? If my pressure gauge has some calibration like this, okay, the cursor is here and this is 0. So consider this to be the atmospheric pressure. Okay, for this gauge pressure, always it calculates from the reference of atmospheric pressure. Next, we will know the absolute pressure. Pressure measured from absolute zero pressure, that is absolute vacuum where there is no pressure. It is called the absolute zero pressure. So absolute pressure is equal to gauge pressure plus atmospheric pressure. Okay, so this is P absolute, or we can show it as P zero pressure. Okay, from this till gauge pressure we will call it as P absolute or the absolute pressure. Okay, so what is the absolute pressure? When you measure, let us consider you measure 1 bar in gauge pressure. Next we have atmospheric pressure of 1.0325 bars. So what will be my total absolute pressure? It will be equal to the sum of gauge pressure plus atmospheric pressure, that is 2.0325 bar. Okay, it is the P absolute. Next, what is the vacuum pressure? Pressure below atmospheric pressure. Okay, so if there is some line, let me consider here. Now here we see that it is P vacuum. So any pressure above atmospheric pressure is termed as gas pressure. Any pressure below atmospheric pressure is termed as vacuum pressure. Now you know that this is the vacuum pressure. Okay, from it is considered from which reference? From the atmospheric pressure. And now which will be the absolute pressure here? This will be the absolute pressure in this case. Okay, for vacuum pressure. Let us now clarify it. If we have a gauge pressure here, then let us consider this as zero pressure zone. If this is the case, this is the atmospheric pressure and this is the gauge pressure, P gauge. Right, now this distance total is the absolute pressure. Okay, this distance is the gauge pressure. Okay, first this. Now let us consider some pressure which is below atmospheric pressure. So we will consider the vacuum pressure. Now this is the same atmospheric pressure. This is the zero line or zero pressure. Okay, which is called the absolute vacuum pressure also, right? Now let us consider a point. Let us say my device showed pressure something which is less than 1.0325 bar, which is less than atmospheric pressure. Then this is my vacuum pressure. Always remember that it is referred from this PATM. Similarly, the gauge pressure is referred from here. And here this is my absolute pressure. Okay, so absolute pressure will always be positive, remember it, because it is taken from zero pressure line. But gauge pressure is positive, vacuum pressure will be negative, since it is referred from this. What is the zero for this gauge pressure? This is the atmospheric pressure. So anything beyond this point it will go negative, so the vacuum pressure will be negative, and above this point the gauge pressure will be positive. Okay, now let us move on to the Pascal's law. We had learned it already in the previous class, but here I want to say a small example. For example, see, this is a bottle. This is a bottle. Here we have a cork. Now atmospheric pressure, we know the fluid pressure, it acts, the pressure is equal in all direction. Okay, the pressure is equal in all directions. According to Pascal's law, pressure applied to a confined fluid is transmitted undiminished, means it is undiminished, means it is equal in all direction, acts perpendicular to the surface, remember, and exerts equal forces on equal area. So you need to learn here that the pressure on the cork on this surface is same as the pressure on the bottom of this jar. Right, first thing what I want to say you is that remember the pressure is equal but not the force. why we know that force is we know that pressure is equal to force by area. So where the area is small, okay, the area is small, the force will also be small. If the area is large, the force will also be large. You won't understand. If you don't understand, let us take a small example. Suppose my area of this cork area is 10 millimeter square. Let us consider 10 centimeter square, and this is 100 centimeter square. Let me take the area. Now let me consider the pressure is equal. My pressure is 50 mm, kg per centimeter square. Let me just take it a small example, right? So I can say that 50 in first case F by 10, and here 50 is equal to F by 100. Let me consider this is F1, this is F2. This is F1 is for cork and F2 is for the bottom jar. Here I can say that F1 is equal to 50 into 10 is equal to 500 kg, and F2 we can say from here is that 50 into 1000, 50 into 100, that is 5000 kg. So we can say that the larger the area, the larger the area, the greater is the force here. Okay, so this is a small calculation which is given in this video. You can just watch it. Okay, now let us move to a topic called Brahma's press. We had learned about this diagram in the previous video. So this Brahma's press, it was invented by Joseph Brahma. You must remember that first to apply Pascal's law mechanically. So we know, we know that larger the area, larger is the force required. Okay, so what he did, Brahma, he did a simple calculation. We know that force by area, just let me change the color of my pen. Okay, we know that force by area, let us consider this one is larger force, is equal to force by area, because the pressure is equal to, the pressure is same in all directions by Pascal's law. So we can say that larger force by smaller force is equal to larger area by smaller area, and this is the forces are proportional to piston areas. Okay, so with application of little force, if the force is very less applied here in this smaller area, we will get a larger output here, larger force output in this larger area. So small force on a small area creates a larger force on a larger area. Okay, next there is another relationship which we must know, the displacement relationship. Here we know that area into displacement, area into displacement is equal to larger area into larger displacement. So here we can, by this method we can calculate the amount of displacement that will be done by the larger area. For example, here A1, let me give a displacement of 1 meter. Okay, then if I give here a displacement of 1 meter, then what will be the displacement here, that capital L, here we can calculate it by this method. Okay, this is a simple example of what we can do. Next, we know that energy is conserved. Energy is conserved also in hydraulic systems. We know that work input is equal to work output. So what is the work? We know work is nothing but force into displacement. So in Brahma's press, what is the displacement? It is, the displacement is this, the stroke length of small piston. This is the piston, right? So this piston, the length it moves is the stroke length of small piston, and this is the larger piston. Okay, so it is the length which it will move, it will be called capital L, and this will be small l. So force, that is force on applied on the smaller piston into distance moved by the smaller piston is equal to force moved by the larger piston into displacement by the larger piston. So we can also say that force can be increased but displacement will decrease accordingly, because F into L is equal to capital F into capital L. See, what it is said here is that if the force increases, L has to decrease to keep this constant, right? For example, see, 10 into L is equal to, let us consider the larger force is 20 and here the displacement is 5. Okay, so what will be the value of L here? It will be 0 0 will cancel and it will be 10 meter. Let us consider for example. But when I go to increase this force, 20 into L is equal to 20 into 5. Let us consider this is kept fixed, F into L. Okay, so these are fixed. So what will be the L in case? It will be 5 meter. So we can say that when we increase the force, the displacement will decrease to provide the same displacement in the other side, the same resultant in the other side. Okay, so this is the conservation of energy. Next, pressure and flow. See, this is a very important topic and you need to understand it very clearly. Very specific topic which we get confused here, pressure and flow. Okay, so here a motor is, a pump is running. Here this is a pump is running and it is providing water. Okay, it is providing water to your house line. So how much pressure will it provide? Will it provide pressure or is it providing the flow? What is the pump doing? With how much pressure the water will come? With how much speed the water will come? What is it? Is it pressure or flow? Very confusing topic, right? See, before moving into pressure and flow, let us understand about hydraulic pump. See, hydraulic pumps are positive displacement type. Pump that is positive displacement type means pump output is constant with constant RPM regardless of pressure. Okay, so when we consider positive displacement pump, we consider that the amount of water at inlet is equal to amount of water at outlet. Okay, or the amount of hydraulic fluid at inlet is equal to the amount of hydraulic fluid by the outlet. Okay, so the quantity is same, the pump output is same with constant RPM. As we increase the RPM, the output will also increase. Okay, so what are the characteristic? First, for this output we must know that there must be good sealing. Internal leakages must be very low. Okay, if there is bad sealing or the sealing is damaged, leakages will be more, so input can never be equal to output. Second, the output volume must be fixed per revolution. Per revolution maybe 1 liter or 2 liter, so this is fixed volume. Second, fluid entering the pump is forced out through the outlet. The fluid is forced out with some pressure, with some flow. Remember now the question that I asked, the pump creates flow, not pressure. So the pump which you are using, you are saying that we need a high pressure pump. It is not a high pressure pump, it is a high flow pump. Second, pressure is generated by the resistance to flow in the system. The more you block the pipe, the more you provide the turns, the more you offer resistance to the path, you will see that the pressure will increase. For example, we will provide the example in the next few topics. Okay, see, flow versus pressure. Flow is the movement. Flow refers to how much fluid is moving. It is the rate at which fluid is moving through a pipe or system. Okay, how much volume, how much water is coming, how much volume is coming out per time. Okay, volume per time. Generally, it is the Q, the flow rate. Okay, so then what is the pressure? Pressure is the push. It is the force that pushes the fluid. Okay, so this flow provides the quantity. Remember, flow provides the quantity, how much volume will be coming out, but pressure provides the push, with how much force it will come out. So it's how hard the fluid is being pushed inside the system. This is the difference between pressure and flow. See, when we turn on the nozzle, when we turn on the tap, what we do, we increase the flow of the system. The quantity of air coming from this tap will increase. But when, for example, for while doing gardening, for watering the plants, what we do is we just put our finger in front of this nozzle. Okay, so the area is reduced, the pressure will increase and the force will increase. The area will decrease, the force will increase and the water will move to a greater distance. The volume has reduced. Remember that flow has reduced, but what has increased here? The pressure has increased here. So here there is a greater distance covered by this water. Now let us consider A tap is fully open without nozzle. We will consider it a high flow because whole water is coming but very low pressure. A tap is slightly open, nozzle is attached. It is low flow but high pressure. Next, tap is fully open, nozzle is partially blocked. There is a medium flow but there is high pressure. This was just an example. Now what causes this pressure? See, pressure is caused by, this is a cylinder here. Let us consider. Okay, so you are connecting it to a hose. So this is a cylinder and this is my piston. A piston, a load is there. You are putting a small bike here. Okay, small bike here. So now the pressure you are the pressure the load on the actuator, what is the load on the actuator is the load of the bike. Okay, so the work done by the fluid in moving this load, this all depends upon the sorry the work done by moving this bicycle upward or to carry this load, it is F into D, force into displacement. So the force here is small. So the pressure always depends on the load on the actuator, how much load is there. Okay, if there is less load, less pressure. Next, with the same arrangement, if I am lifting a car here, the pressure will increase because the load will increase. So the load on actuator determines the pressure. Second, restriction in the system, how many bands are there, how many valves are there, these all provide resistance to the flow of the. So if there are several bands here in the pipe which I have provided, the flow will decrease. Remember, the flow will decrease but the pressure inside the system will increase. So many bands can also burst the pipe, can collapse the pipe. Why? Because the pressure has increased too much and these pipes are unable to take this pressure. Therefore we see that whenever we need in a good hydraulic system, we try to reduce the bends in it to reduce the pressure inside it, because we don't want it to go in a turbulent way. Right, now the key point is this: more resistance, more pressure; less resistance, less pressure. Okay, now for the flow, for example, in our hydraulic system, flow is created by the pump which you are using to pump the hydraulic fluid. It creates flow, and pressure is created by the resistance. Flow moves the fluid through the system, but pressure enables force generation. And at constant RPM, the flow is constant, but pressure may vary. It may vary on the load. Now, before moving forward, let us take a small example of the positive displacement pump. What is the difference between the positive displacement pump and the negative displacement pump? As we studied, a positive displacement pump is a fixed volume pump. A fixed volume of fluid per cycle regardless of pressure, means its output volume is fixed. Okay, anything that it takes in, it goes out. The quantity is fixed. But how does it work? See, it traps a specific amount of fluid. For example, here I am using a pump. It traps this fluid and here is a wheel, let us consider, or a gear we can consider. It traps the fluid and the gear rotates and it throws out the same quantity of fluid from inlet to outlet, and this is directly proportional to RPM. With increased RPM, the wheel will rotate at a faster speed, it will trap the fluid at a faster speed, and also the output will be higher. So for positive displacement pump, we know that at constant RPM is constant, okay, the output will be constant. Next, characteristic: high pressure capability. It can provide high pressure. It is very consistent and accurate flow and used for viscous fluid. Okay, since non-viscous, we will learn viscous and non-viscous. Remember that viscous is a little heavier, a thicker density fluid, okay, which shows some resistance to the backflow. Next, it cannot run against a closed outlet. In closed outlet, we cannot provide this fluid because we need a constant output, right? So here we can see as an example, this is the inlet here. Let me just change the color of my pen. Okay, so this is the inlet here and this gear is running. With this gear, it is holding some fluids in this zone and this fluid is moving outwards. Okay, similarly this gear also, it takes the hole and moves outward. So what are the examples? Gear pump, piston pump, screw pump, vane pump, diaphragm pump. These are all of the examples. And applications are hydraulic system, oil gas industry, chemical dosing, and food processing. Now coming to the non-positive displacement pump, here there is some losses with the flow, so the output cannot be determined. Okay, the flow rate varies with system pressure, and it is not self-priming, and the pump does not cannot pump very high viscous fluids. Okay, remember that it is opposite to the positive displacement pump. Here there are impeller blades, and it all depends on the fluid movement depends on the pressure and resistance of the system. So here see, this is the centrifugal pump. Here the fluid is moving inside this through this way, and some of the fluid there are certain losses, and some of the fluid is moving out, so we cannot capture the output here. Centrifugal pump, axial flow pump, mixed flow pump, all are the examples of non-positive displacement pumps, or better known as dynamic pumps. Now let us come to the differences. Flow type: there are positive displacement, non-positive displacement. For positive displacement pump, we know that constant per cycle, and but non-positive displacement, it varies. High pressure can be handled well by positive displacement pump because it locks the unit. Okay, it locks the hydraulic, and it can provide high pressure. But this cannot provide high pressure. This can only provide good flow. Self-priming. Self-priming means to lift the water, means to remove the air and lift the water. Okay, for example, when there is in the ground, we can say the water level is lower. Okay, there is, you have turned on the motor, and the pump is not dived into the water, so it has to first remove the air, then suck the water and make the water come out from the outlet. Okay, the work of the pump is, one minute, the work of the pump is similar. So it is self priming because it locks it. Okay, there is no leakage, but it cannot work, it very rarely works with self priming. For moving the air out, it needs a good leakage proof container, which is mostly not available in non positive displacement pump. Examples we have learned in there: viscous fluids, it is suitable for viscous fluid, but non positive displacement pump are not suitable. For low flow, efficiency is very high in positive displacement, efficiency is very less in case of non-positive displacement. Okay, now let us look at the flow paths in hydraulic process. See, in case of any hydraulic system, here is a pump. Okay, we will study the hydraulic diagrams later. This is the pump. So I have two cylinders here. What can be the arrangement? I can provide them parallelly supply, or I can provide one cylinder here, and from this the output will go to the other cylinder here. Okay, so there are two types of connection we must remember. The first one is the parallel flows path, and the second one is the series flow path. So first let us consider the parallel flow. Let us consider, here there is a load of 10 Newton, and here there is a load of 5 Newton. So when in case of parallel flow path, see, the fluid pressure will depend on the lowest load or the lowest pressure. So the movement will be in the least resistance path. So the work will be first done on this 5 Newton. This 5 Newton of load will be first lifted off, and then if there is built a pressure inbuilt, if the 5 Newton has reached its high optimum pressure and a pressure is built inside the system, the pressure rises again, then if it goes 10 Newton, then only this will work. Remember, so the first thing to remember is that fluid flows through the path of least resistance. If two parallel paths have different resistance, fluid prefers the easier path. Pressure builds only enough to overcome the lower resistance. Okay, so the pressure builds for overcoming the lower resistance, not for the upper resistance. So after the lower resistance has been built, and if there is more resistance further, the pressure will increase gradually to 5, 6, 7, 8, 9, 10, and after 10 only it will be activated. If there is some pressure relief valve here, or the pressure does not rise, in this case this will never work. Okay, if two actuators with different loads are connected in parallel, the actuator with the lighter load moves first. The other actuator may not move or lags behind. Remember, may not move means it may move or may not move. The synchronized motion is not possible in this case, parallel flow. Now let us look at the hydraulic. Let us look at the series flow. In series connections, when For example, let us consider that here is the pump, here is the hydraulic cylinder, a piston, and then again from this there is an output. Here is another cylinder. Okay, so the total pressure here will add up, and then from here there is a single output. Let us consider here weight is 5 Newton, here weight is 10 Newton. So what will be the, or here also let us consider 15 Newton. So how will this system work? First remember, the pressure is always calculated from the output. In output there will be zero pressure. Zero pressure, why? Because the water, the fluid, hydraulic fluid come out with, there is no blockages prevented here, so the water, so the fluid will come out directly. There is no resistance, it will be zero pressure. Next, coming from the, coming to the second pump here, we can see that only one pressure needs to be built, which only we have to work with this pressure 15 Newton. So here the pressure will be 15 Newton per any area provided. Okay, next when we come here, the pressure will add up. 10 plus 15, that is 25, means here at this point it has to work with two pressures. This pressure will also act, this pressure will also act. 10 plus 15, that is 25 Newton pressure will be shown in this gauge here. Okay, in this gauge here it will show 15 Newton, and in this gauge it will show 0 Newton, right? So in a series connection, resistances add up. Total pressure is equal to sum of all pressure drops across components. To move the load, the pump must overcome load pressure. Okay, so this is the load pressure, the 25, 15, 0. These are all load pressures. Pressure drops across valves and other components. If two actuators with different loads are connected in parallel, the actuator with lighter load move first. We have learned it. The other actuator may not move or lag behind. Synchronized motion is not possible without special method. Pump must generate higher pressure than load alone requires. More energy is consumed due to. So these are all these are provided for the parallel circuit, not for the series. So in case of series, remember that the sum of pressure will be equal to the load pressure. Okay, and this is in case of series. Now in series flow, so this is duplicated page, just a minute. Okay, so now let us come to the difference. Here we'll understand. For parallel flow path and series flow path, the flow path offers least resistance, and all resistance in this path series flow add up. Next, pressure is equal to the lowest needed, but we learned that in series it came to be 0 plus 10 plus 15 something, or 25 Newton it came, right? So here is the sum of all drops, it is summed. But in case of pressure, we learned that it was around 5 Newton which was to be overcome. Now actuator behavior, it moves unevenly. Okay, there is no synchronism, but here there is a good synchronization, and the actuator moves in order. Synchronization is not achieved, synchronization is more controllable. Energy use, lower energy use, but inefficient for control. Here is higher energy used due to more added resistance. Next is the speed of the actuator. Okay, actuator is the cylinder here we consider, right? So what does this actuator depends? The flow rate, which we learned, it is nothing but the volume per unit time. Okay, the flow rate, the rate of flow at which the flow of the liquid, and the size. So the speed, the velocity depends on Q by area. Okay, so the flow rate divided by area. Speed of actuator, or the movement, the motion of the speed of the piston in millimeter per second, can be determined flow rate into the actuator, that is liter per minute, or divided by cross sectional area of actuator. Remember that there is no effect of pressure on speed. The piston will not move. We learned it. Okay, so it depends on the flow. Okay, so pressure only provides force with how much impact it will come. Okay, next, the speed of the actuator. To move an actuator, oil must fill the internal volume. Okay, so this is the cylinder and this is my actuator. To move this actuator, the oil must fill of the volume. Okay, after filling up only, this is the hose or inlet. Okay, after filling up the whole volume, only the actuator will move. More flow, faster movement. Larger area, more volume to fill, so movement is slower. Okay, remember this is a very important concept. The area is larger, you require more oil to fill up this area. Here, this is the larger tank. Okay, here this is the larger area tank, so the speed will definitely be slower as compared to a smaller tank, because here the fluid will flow up fast, here the fluid will take time to fill up. Okay, larger amount of fluid is also required, movement will be slower at same flow rate if flow rate is equal to same. Next, power and efficiency. Power is the rate of doing work. We have studied in mechanics. In hydraulics, work done when force moves an object through distance is called work is done when force moves an object. We have learned for work is equal to F into D. Okay, so power is equal to work upon time. So units of power are horsepower and kilowatt power. Remember that HP is equal to PSI into GPM into 0.00583. What are all these? These are PSI, it is the unit of power, pound square inch, GPM gallons per minute into 0.00583. Here kW is equal to bar into liter per minute divided by 612. Just some formulas which you do not need to memorize all of this. Okay, but how are these calculated? I have provided you one just a simple option. Now we also know that efficiency is equal to efficiency of any hydraulic machine is equal to ideal power divided by actual power. Actually, here I think there is a mistake here. The efficiency is not this. Efficiency is, remember that efficiency is equal to actual power that they provided and by ideal. Okay, so this is the efficiency here, so don't memorize this concept. Efficiency is equal to actual by ideal. Okay, so actually let us provided the let us take into concept that the ideal power is 15 kilowatt and actually it is providing 10 kilowatt, so the efficiency will be equal to 10 by 15, that is 2 by 3 is equal to 0.66%. Okay, or 0.66 or 66%. Next, torque in hydraulic motor. Torque is the rotational force created by hydraulic motor. Okay, so this is the motor and this is the torque where it turns against a load. So torque is nothing but turning effect. It is the turning effect which is provided, the rotational force that is being provided by the hydraulic motor. Torque in pound and newton per centimeter, these are the formulas provided. That's all for today, and with this we have completed the second class of hydraulic, the industrial hydraulics. In the next class we will dive into much better concepts: viscosity, the hydraulic fluids, and the characteristics of hydraulic fluids. All are most of much important for the basic understanding. Hope you like this video. So if you liked us, please subscribe to us, please provide us comments, do share with us, and to support us you can scan this UPI, scan this QR code, and show some little support, or you can go visit this page here provided. So with this you can provide us with little support to continue making such videos, because we still have a lot of videos to make. With your love and support, we think we can do much better. Thank you, have a nice day.